So, today is the session for solving problem, and maybe next session also will be on problem solving, and maybe next section will also be on problem solving. So, I start with a problem which is based on this book by Klepner and Kolonkov, and this particular problem is based on question number 4.13 of Klepner, and it says that the potential of a particle of mass m by 2 is given by u equal to epsilon, then r naught by r to the power 12 minus 2 r naught by r to the power 6. The questions are: A, sketch the function. The second part is find the equilibrium separation. Find the equilibrium separation of the particle from the origin. And the third part is find the frequency of small oscillations about the equilibrium point. So, it is based on, it is not 4.13 of that book, it is based on that. Okay. Essentially, it is a one dimensional problem. You are talking of equilibrium position, you are talking of frequency of oscillation about that equilibrium position. So, it is essentially a one dimensional problem, and you may be wondering why m by 2, why not m? So, that will become clear after a few lectures. So, sketch the function, sketch this function. So, I have to write r and this u, and how do I sketch? The first thing is that are there points where this u is 0. So, I want to know whether this curve cuts this r axis or not, and if it cuts, then at which points. So, to sketch, let us do all those exercise. If u is equal to 0, if u is equal to 0, that means r naught by r to the power 12 is equal to 2 times r naught by r to the power 6. So, if I take the sixth root, it is r naught by r to the power 2 is equal to 2 to the power 1 by 6, and then here r naught by r, right. I am taking sixth root, the whole thing to the power 1 by 6 here. So, that will make it 2, and 1 by 6, this will be 1, and this will be 2 to the power 1 by 6, and that means r naught by r is equal to 2 to the power 1 by 6. So, r is equal to r naught divided by 2 to the power 1 by 6. So, you get only one value, you get only one value of r where u is 0, and that value is slightly less than r naught, because 2 to the power 1 by 6 will be more than 1. So, you are dividing by a quantity which is more than 1. So, this will be smaller than this. So, on this graph, if I need more space. So, suppose this is my r here, this is u here, and this point is r naught, and this r which makes u equal to 0 is somewhat less. So, suppose it is here, that is one. It will cross this r axis only at one point. Now, what happens if r is very small? If r is very small, so this is u. If r is very small, you have 1 by r which is very large to the power 12, and here you have 1 by r to the power 6. This is also very large, but this thing is the square of this. 1 by r to the power 6 is also very large, but then square it, it will become very much larger, and this will be this factor. That means, for very small r, this will be much larger than this, and so this whole quantity is positive, right, and going to infinity. For very small r, this will go to infinity, this is also going to infinity, this is also going to infinity, but this is a much bigger infinity, and the whole thing is positive and going to infinity. That means, for very small r, it is coming from here, that is one. Then you have what happens if r is very large. If r going to very large values, this is going to 0, this is also going to 0. So, ultimately it has to go to 0. So, that is another information. And then what you have is that where are maxima and minima. So, we have the information that for small r it is very large, for large r it is going to 0, and then in between what happens? For that, let us look for the maxima minima. So, du dr, let us look for du dr. Now, du dr, if you differentiate, it will be epsilon here, then 12 times r naught by r to the power 11, okay, 12 times r naught by r to the power 11. That means, I have differentiated this term with respect to r naught by r, and so I have to multiply by differentiation of derivative of r naught by r with respect to r, which will be minus r naught by r square. So, it is minus r naught by r square, this. So, the first term we have differentiated. Come to second term, minus 2 into this 6, that is 12. So, 12, and then r naught by r to the power 5, right, 6 is here. So, 6 will come to this side, 2 into 6 will be 12, r naught by r to the power 5, then differentiation of r naught by r with respect to r, which will be once again minus r naught by r square. That is du dr. So, let me write it in a somewhat more manageable fashion. Du dr is equal to epsilon and then square bracket. Now, it is 12 here, 12 you can take out if you so wish. So, 12 I can write somewhere here, let us write it somewhere here. Then it is minus r naught to the power 12. So, minus r naught to the power 12, and then r to the power 13, right, r to the power 13. So, divided by r to the power 13, and then here you have plus, and 12 we have already taken. So, r naught to the power 6. So, plus r naught to the power 6 and divided by r naught to the power 8. r naught to the power 6 divided by r to the power 8 divided by r to the power 5 from here and r to the power 2 from here. So, r to the power 7, this is r to the power 7. This is du by dr, right. Now, if this is 0, if du dr is 0, that means r naught by 12 divided by r power 13 should be equal to r naught 6 here and r to the power 7 here, and therefore, r naught to the power 6 divided by r to the power 6 should be equal to 1, r should be equal to r naught. Because I know that in the beginning it is very high and the end it is 0, going to be 0, and there can be only one maximum or minimum. So, that has to be minimum, that cannot be a maximum. So, it will decrease, it has to go to this point where it crosses this point, it becomes negative there, then it has to be a minimum here if it wants to reach this 0, and that minimum must occur at r equal to r naught, and then it will go and then it will gradually approach 0. So, that is the kind of sketch we have. This is the kind of potential energy function. If the particle is somewhere here, the potential energy is positive. If the particle is here, potential energy is 0. If the particle is here, then the potential is negative. If the particle is here, it is maximum negative, and then gradually the potential energy again increases, right. So, that is A part. B part, find the equilibrium separation of the particle from the origin. So, equilibrium positions mean the force is 0, it stays there, that is the equilibrium position. That happens when this potential energy is minimum, because force is given by negative of du dr. So, if force is 0, du dr is 0, and therefore, the equilibrium position will be at r equal to r naught. So, this is also done, the equilibrium position will be this will be the answer, r equal to r 0, this is that equilibrium position. What does that mean? If you put the particle at r equal to r naught, okay. If you put the particle at r equal to r naught, it will stay there in equilibrium, it will not move. So, that is the meaning of this. This is essentially one dimensional motion. If it is two dimensional motion, r equal to r naught means a circle, okay. But here it is this equilibrium position, the force is 0. Then the C part, find the frequency of small oscillation about the equilibrium position. So, if the particle is here and the energy is just this, if this is the energy, if this is the total energy, and total energy is equal to the potential energy, total energy is equal to the potential energy, then the kinetic energy is 0 and the particle does not move. But if the energy is more, if the energy is more, then the particle can move, and we have already discussed these are the turning points. These are the turning points. This is, let us say, R1 and this is R2, and the particle with this energy, it will go from here to here, here to here, here to here, here to here. That means, from the origin the distance will change and it will stay between R1 and R2. So, these are the turning points. So, this is the kind of motion, but frequency of small oscillations, that means the energy is such that you have you are using only this much. So, your energy is very close to that required for equilibrium. So, somewhere here, so it goes in a oscillation here, and if it is small, then this portion can be approximated to a parabolic curve, and then it will be SHM. And we will see, I have to do some calculations, I can perhaps do it here, that for small oscillations it can be treated as an SHM, and then we can get the frequency from the SHM equations. And how do I do that? I go for this expansion of u around this point r naught. Okay. So, u is equal to, this is called Taylor series. It says that if you have to get u as a function of r and you have a point r naught which is very close to it, you can write it as u at r naught and plus du dr at r equal to r naught and then multiplied by r minus r naught plus then half of second derivative d2v dr square evaluated at r equal to r naught and multiplied by r minus r naught square, and similarly higher order terms coming in there. And if r is very close to r naught, perhaps you would like to neglect this r minus r naught square term in comparison to r minus r naught term here. You do have r minus r naught cube terms and fourth power and fifth power, but if this separation is small, if this quantity is small, then you can neglect higher order terms. Now, in our case du dr at r equal to r naught is 0. This is r equal to r naught and here du dr is 0, and therefore, this term is not there, and so I cannot neglect this in comparison to this, and so I have to evaluate this. We can do that u. So, we can do that, and its du dr is here. So, let us calculate what is d2u dr square equal to 12 epsilon minus r naught to the power 12, and then you have to differentiate r to the power minus 13. So, minus 13 here and then r to the power minus 14. So, r to the power 14 in the denominator, right. I have written minus, I have written r naught to the power 12 which is constant, and then I have to differentiate. So, I am differentiating r to the power minus 13. So, minus 13 r to the power minus 14, r to the power minus 14 is written as r to the power 14 in the denominator. Now, come here plus r naught to the power 6. So, this is r naught to the power 6, and then I have to differentiate r to the power minus 7. So, minus 7 here and then r to the power 8 here. So, that is the differentiation. So, let me, and it has to be evaluated at r equal to r naught. So, if I write r equal to r naught, so this every r becomes r naught, r equal to r naught. Then what happens? Then it is 12 epsilon, this minus and this minus is plus r to the power 12 divided by r naught to the power 12 divided by r naught to the power 14. So, it is r naught to the power 2. So, it is 13 divided by r naught square, the first term. The second term is minus here and 7 here and divided by r naught square. So, this is 12 epsilon into 6 divided by r naught square. So, it is 72 epsilon divided by r naught square. Now, look at this term u r is equal to u r naught and then plus half of this quantity d2u dr square at r equal to r naught. So, that is 72 epsilon divided by r naught square and then r minus r naught square. Compare with u x equal to half k x square. This is our SHM equation. Potential energy of a particle undergoing simple harmonic motion F equal to minus k x. So, that k is here, the potential energy is given by half k x square. There we choose 0 of potential energy at x equal to 0, right. So, around that, and you know potential energy is always arbitrary to an additive constant. So, it does not matter where I take my potential energy to be 0. So, this is just a constant shift, okay. And then this is the equilibrium position, and here this x is also from equilibrium position. So, separation from the equilibrium position square, separation from the equilibrium position square, same story, and this does not matter. You can take any point and say that okay, my 0 is here, potential energy 0 is here. So, a DC shift can always be done. So, it is identical to this. This will be an SHM. If this is the equation, this is HM. Of course, this is an approximation because we have neglected the third power, fourth power and sixth power, but if r is close to r naught, we can do that. And so, this motion will be approximately SHM. For small change in energy, the motion will be approximately SHM, and what will be the frequency? So, for SHM you know angular frequency square root of k by m. So, the same equation here, in our case omega is equal to square root of k. In place of k, I have the 72 epsilon naught by r naught square. So, 72 epsilon naught by r naught square and divided by m, and mass of the particle here is m by 2. So, we divide by m by 2. So, I put m here and into 2 here, and 72 into 2 is 144, a perfect square, square root is 12. So, this is 12 times epsilon naught divided by m r naught square. Okay. So, epsilon naught is in our habit, we when we do electrodynamics, we write epsilon naught so many times. So, this is the angular frequency, and you know the frequency as such is this angular frequency divided by 2 pi. Let me take one more question, and this will be proper two dimensional central force motion. And the question is based on 9.2 of our Kleppner-Kolonkov book. A particle of mass m, moves under an attractive central force F of r is equal to minus k r cube. The angular momentum is L. The angular momentum of the particle, and obviously about the origin. Is L. The maximum distance of the particle the maximum distance of the particle from the origin is double the minimum distance and the question is find this minimum distance, find this minimum distance. Okay, so force F is minus k r cube. So, write what is potential energy U. U will be what? You have to integrate. So, k into r to the power 4 divided by 4. This will be the potential energy. If you differentiate it with respect to r, you get k r cube, and put a minus sign, you get the force. So, this is potential energy. What is V effective? We have used this terminology. V effective, it is L square by 2 m r square, and then the actual potential energy, which is plus k r to the power 4 by 4, k r to the power 4 by 4. This is the effective potential energy. And if we draw the potential energy, how will it look like? If this is R and this is V effective, and if I draw this, if you take very small values of R, this is negligible, very small value, so it is going to 0, very small values, this is going to infinity, so it comes from infinity. All the time it is positive, r square here, r 4 here, all the time it is positive. I do not have to find the point where it crosses this r axis. And of course, I can look at the large r values. For large r values, this will be 0, but this will go to infinity. So, it starts from infinity and it goes up to infinity. What happens in between? So, look for the maxima minima, V effective, and then differentiation of this with respect to r. So, if you differentiate, you have minus L square by m r cube, this term will always occur. So, I remember it, and then here when you differentiate, it will be plus k r cube. If it is 0, if it is going to be 0, then you get L square by m k. L square by m k is equal to r to the power 6, the 6th power of this. This is the place where this will be maximum or minimum, and the only one value, you get only one value of r. So, only one maxima or only one minima is possible. This is infinity, this is infinity, it is always positive, it has to be a minimum. So, your function will be something of this type, and this will be the minimum. Now, it is said that the maximum distance of the particle from the origin is double the minimum distance. So, that means the energy is something like this. This could be the total energy, and here are the turning points. This is that minimum distance, let us say r naught, and then this is another turning point, and this will be 2 times r naught. Okay, if this is the total energy, then the particle cannot come this side and cannot go that side. It has to remain in this, so that half m r dot square is always positive, it cannot be negative. Here that r dot is 0, here this r dot is 0. So, these are the situations. You have to find the value of r naught. How do I get that? At this point, and at this point the total energy is same as this effective potential energy. That is why that half m r dot is 0. Total energy is half m r dot square and plus L square by 2 m r square and plus u of r, potential energy here V or u, I do not know what I have written. So, this is the kinetic energy and this is the potential energy, but then we combine these two and write this as V effective. So, the total energy is your effective potential energy and plus half m r dot square. So, here that r dot is 0 and u is same as the V effective. That means, V effective here at r naught, and that is L square by 2 m r naught square. Okay. At this point, what is the effective potential energy at this point, minimum distance? So, r is equal to r naught. So, I am writing r naught here and then plus the potential energy at r naught, which is equal to the effective potential energy at this point. So, effective potential energy at this point is L square divided by 2 m 2 r naught square and then plus effective potential energy I am writing at 2 r naught, like this, like this. So, I have written u here, so I should have written u here, I should have written u here, I should have written u here, and yeah, V effective is fine. Okay. So, this is u at r. So, this is a situation I can write L square 2 m r naught square plus u at r naught. What is u at r naught? K into r naught to the power 4 divided by 4. So, k into r naught to the power 4 divided by 4 is equal to L square divided by 2 into 2 is 4, 4 into 2 is 8. So, 8 m r naught square plus this is k by 4 and then 2 r naught power 4. The potential energy at 2 r naughts, it is this. So, this is 16 by 4 is 4 here. So, I have this L square minus 2 m r naught square, this one, and minus this one, minus L square by 8 m r naught square is equal to, this is 16 by 4 is 4, 4 k r naught to the power 4 and minus k r naught to the power 4 by 4. Alright, so easy to calculate L square by 2 m r naught square and then you have 1 minus 1 by 2 I have taken, so 1 by 4. Correct, 1 by 8 here, 1 by 2 is here and 1 by 4 is here, and this side k r naught to the power 4 and then you have 4 minus 1 by 4. Alright. So, this is 3 by 4, this is 3 by 4. So, 3 L square divided by 8 m r naught square, and on that side it is 15 by 4, 15 by 4 times k r naught 4. That gives you, let us take this r naught square on this side. So, this will become r naught to the power 6, r naught to the power 6 equal to, and everything rest will be on the other side. So, this I can make it okay, let me write. So, 3 L square by 8 m, 3 L square by 8 m. From this side I had taken this r naught square there. So, it is 3 L square by 8 m, and from that side I have to bring this thing. So, this 15 k will come in the denominator. So, 15 k here, and this 4 will go in numerator. So, 4 will go here. So, this will be what? 3 and 15. So, 5 here, 4 and 8. So, 2 here. So, it is L square and divided by 10 km, 10 mk. and therefore R naught is equal to, minimum distance is equal to 1/6 power of this, that means it is L square by 10 mk to the power 1/6, and that is the answer. 1/6, that is the answer. L is given to us, mass of the particle is m, and k is given to us, a particle of mass m. So, that is our minimum distance of the particle from the origin.